Okay, I wanted to do a very quick introduction to Thursday's tutorial, which is on the power transistor. This is the first time that we're going to be modeling current and charge distribution and diffusion and accumulation. So I just finished a video where I talk about the way that COMSOL and multiphysics in general considers current diffusion as a conservation equation over a three-dimensional domain. Please take a look at that one, right? But here what we're going to do is we're going to put that into a model coupled with heat transport and heat accumulation because we're powering this transistor. We don't want it to overheat. Now, when we go into this, here we've got our electric circuit physics mode. And if we expand that, what we can see is the equation here. Now, a lot of people will write the flux like this as sigma, which is our conductivity, times E, right? Whereas the previous video, I've been talking about negative grad V. The electric field E is exactly equal to negative grad V, hence the line below it. So just do be aware that it's going to talk about E, but E is bolded here because it is a vector quantity, and here is how it's being calculated down here, just as a reminder there. Okay. Current conservation, we just spoke about that from the previous one. There's nothing really too complicated about this model, with the exception of this terminology, normal current density. Okay, so usually when you're talking about electric circuits, you would talk about current. Again, this is the idea because typically you're talking about something like a wire where you don't have to worry about the cross-sectional area. But now that we're in 3D, now we do need to worry about the density. So that's where that terminology comes in, the current density. But if you integrate over that area, then you're going to get your total current. Okay. What I really wanted to point out to you here, there's nothing really too confusing, is this new node, which is the multiphysics node down here. The multiphysics node is a way to explicitly state that two types of physics are being coupled together. So in a previous tutorial, we talked about the chicken patty and how it sounds like a joke. No, we modeled the chicken patty and how the evaporative flux carried away its latent heat of vaporization. This is a different way to couple in different types of physics, where now it's the Joule heating. So it's the current which is moving through this resistive material and generating heat as the charges are kind of colliding and being resisted. Okay, so these are the equations here. Sometimes it's nice to look down at that. So Q, the heat source, is J dot E. You might have learned that the power generated, the heat source, is equal to the current times the voltage. Again, that voltage is actually voltage difference, so that should be delta V. The current is also the negative charge, so those negatives cancel out and you just get J dot E. And then it's also put into, at the same time, the heat equation up here. So just through the single node here, you've actually added terms into your heat system. Okay? It is exactly the same as going up here, right-clicking, adding a heat source, and saying that this was the current density times the electric field, right? You could put it in here and it would be mathematically exactly identical. So it's a nice way for COMSOL to set it up and to explicitly show you what's happening, but it's not necessary to do it that way. You could actually do it, you could actually put it in manually.